Okay, hello, good evening. Hope you're having a good day. Well, I'll be making some videos over the next couple of months uh, on the use of structural engineering software. In recent times, we have collapse of structures, which I'm sure many of you are aware of in Nigeria, of a 21-story building. I'm not here to talk about the event, but I actually took it upon myself to share what I've discovered when using some of the structural design and analysis engineering softwares. So the first software I would like to probe, to examine, is Prota Structure. I'm sure that if you check the engineering field in Nigeria here and all over the world generally, you will agree that Prota Structure or Orion is widely used in the engineering space. So that's why I'm taking Orion as my first software that I probed. Now, if I'm using the term probe, it means I'm checking the inner working, as the title of the video says, inner working of Prota Structure. So, and the first element I'm taking is slab. So I'll be going through what the software is doing, and I will also compare it with our manual design method. Now, this is a slab that I sketch, and this is the dimension. We have the longer side, which is y, and the shorter side, let's say, is x. So it's 5.2 on the y side and 4.2 on the short span. This long span, short span. And from the code, I'm assuming that my slab is not continuous. That means it does not continue on this edge, and it does not continue on this edge, and it does not continue on this edge, and it does not continue on this edge, which means all four edges are discontinuous. That's the case. And if you check the code, that's case 4. Now, to help us, I have modeled and run the design in a software that runs on QBasic. Is made by engineer Victor Oyenuga, the foremost engineer in Nigeria. He has contributed largely to the development and advancement of civil engineering practice in Nigeria. Is well respected. So I have used the QBasic software to run the design. So this software actually is not much different from when you are doing your manual design. So I have used the software to run the analysis for this sketch. So this is my slab, 5.2 by 4.2. So this is the self weight, which is 3.6, partition allowance 1.0, finishes 1.2. Now, another thing I want to stress is the intended use of the structure. I've had cases where during a training or a brainstorming section with some colleagues, and they ask me, how did you get this imposed load? Now, there's a code for action on structure. This is the code for action on structure. So from this code, And if you check some textbook references, it's there also, where you have the categories of structures and the recommended uh, uniformly distributed load on those floor of that structure. So I want to stress that for any design that you are undertaking, always make sure you have your code with you. Always make sure you have your code by your side. So the intended use of the structure determines the enclosed floor load. So for a residential, it is 1.5 enclosed floor load, but for commercial building, the life load for offices will be different from a commercial building that is meant for fitness, let's say gym. So it will be different. So this code BS 6399, I'm relating it with BS 8110. So but there are national annexes for BS code now that states the BS preference with regards to the Euro code. So I'm not here I'm not using Euro code in this case. I'm using BS 8110. So that's why I'm stating the loading code, which is BS 6399. So imposed load for residential is 1.5. For a gym, commercial structure, for a gym, it will be different. For offices, it will be different depending on the use. You go and check the code and use the recommended value. So this is my uh, accumulated dead load, and this is my imposed load, and this is my design load formula 1.4 GK, which I'm sure many in the practice is aware of. So this is my load, design load, 11 kilonewton per meter square. So I like I said, I have run the design using the Q basic. Now I use 20 as the strength of concrete and 380 as the strength of the steel. Now another thing I want to stress is that the strength of steel in the Nigerian market in recent times is of questionable strength. So what I mean by that is that by the time you pick a sample of your reinforcement and you go for tensile strength test, you discover that most of the reinforcement in the market is of low strength. I take a case of a senior colleague of mine executed a project in Ibadan, and he said after they finished the structure, you know, while the construction was ongoing, they took the reinforcement that they used for testing. So the result was not yet uh, delivered to them. In the process, they finished the construction. So after I think they were at finishing stages when the result came, and the design for the structure was based on 410 Newton per mm square. But when the result came, they found out that it was around 200 and something that the result brought back for the tensile strength. In fact, he was shocked. So, and also again, the diameter of the reinforcement that's in the market is also uh, not complete. What I mean by that is that where you're supposed to have 12 dia, by the time you use your caliper to check it, you discover that they are lower than 12 mm. 16, you might be getting 14 for 16 dia bar. So it's just unfortunate we find ourselves in such situation. So in light of that, I reduced the strength of the steel to 380, which was what we were using before we switched to 410. Now that doesn't mean you can't get uh, steel strength of 410, 460. It depends because we have some reinforcement that are imported from overseas, and those ones actually meet. In fact, I've seen a case of 500 in one of the project I was involved in way back some years ago. So that's the case. Then 150 depth, and this is the case two-way slab case 9, two-way slab case 9. So I have modeled the same slab in Prota Structure 2021. Now there's a disclaimer. I do not claim to own a valid license for Prota Structure. However, I subscribed for 15-day trial, and that was the period I used to test uh, the things I'll be talking about when it comes to the inner working of the software. Once again, my aim is to show you some of the things I discovered in the software in relation to if you are running your design manually or using QBasic software. So the essence is that you don't leave your design totally to the software, assuming that okay, the software knows what it's doing. Yes, they've made the software in such a way that it automates the process, but as an engineer we shouldn't leave it to the software to just give us a result, and we go ahead and say okay, yes, I've done the right thing. It goes beyond that. Our training as an engineer goes beyond uh, just letting the software do its thing. We have to probe, because the thing is that we idealize structure as civil engineers. And when we idealize structure, we are saying that we are predicting that our structure will behave in a certain way. That's the purpose of idealization. So when we idealize, if I idealize something like this, which I'm saying is simply supported, my movement will be like this. It will be zero here, it will be zero here, then I will have my maximum movement at the mid span. Now if I idealize like this, if I idealize like this, if I idealize like this, I'm saying my structure is fixed on this end. It's not simply supported. So my movement will be like this. So I will have movement here, I will have movement here, and I'll have movement here. So if that is my idealization, so I don't expect you know that you just jump into the software and say okay, this is the slab, we place beam, we place that, and and that it will just come out fine. With what I've just showed you now, with this case and the initial simply supported case, you can see that there will be fixed end movement here, and there will be span movement here. Of course, you have less movement in span in this case, and you have higher movement in the case of simply supported. So what I'm saying in essence is that when you come up with your general arrangement drawing, you are predicting, or you are assuming that this is how you want your structures to be to be arranged and to behave in a certain way. So you that assumption is the same thing you should take into the software. Now, when you take that into the software, it's now very important you probe what the software is doing, whether the software is actually, doing what you want it to do. That is, the software is analyzing the structure the way you want it, the way you have idealized it. So when you leave it totally to the software without taking this into consideration, then you might be doing something wrong. So my aim basically is to show you the inner working, what is happening in the background of this software as regard to your design. And I'm sure it will be very helpful by the time you see this video and the other ones that I'll be making element by element. Now, again, I won't take you through the process of modeling. I'm sure you can find enough videos on YouTube to help you in that regard. There are wonderful videos out there on modeling and analysis. So let's quickly go to the result of the design that I've done with the QBasic. Now this is the LX, which is 4.2, and this is the LY, and you can see the moment coefficient that is picked. So in this case now, in this my design with this software is saying that there's no movement here, which is 0. So this is the 0 coefficient, and this is for the span. So for the short span and for the long span, this is the coefficient, and this is the coefficient for the span. Remember, we are doing a two-way case and case 9. So this is the moment that was generated for the span, and this is the continuous edge. It's saying there's no movement. It's now recommended minimum area of reinforcements in this case. So same thing in the long span. It's saying span is 10.8, and this is the continuous edge. There's no movement, 0, and this is the minimum area of reinforcement. So it's saying 0 here, 0 here, whether it's short span or long span. That's what it's saying. But now in this case, you have movement here, and you have movement here in this kind of idealization, and which is what is being modeled in the software. So it's assuming that this end is fixed into this beam, these columns. So like I've said, I've modeled it. This is the slab. Let's check the property. This is the slab property. This is 150, and this is case 9. As you can see, this is the load on it, 2.2, the dead load, and imposed load is 1.5, which is the same thing as what I have here. If you sum this up, 2.2 with the self weight, which is also showing here 3.6, so you can see that we have modeled exactly what we have in our sketch. Now, one thing I want to stress, and which many might not take cognizance of, is that by the time I'm inserting this slab, now if I click, let's say I have, okay, let me quickly do something here. Let's say I have one column. Oh, I'll have to put another listing. I don't want to do that. I want to make this video as short as possible. Let's say I've inserted this column, this beam, and I'm putting this slab. Now, chances are that by the time I click this slab, now you can see that it's showing me as 1, which is case 1. Now, case 1 is different from case 9. Now, if I click this slab and say it's inside here, and I run the design, by the time the software picks coefficient, the coefficient will be different. And in that case, what I've noticed that you have lesser moment as it should be. So always make sure you set slab type automatically. That means in cases where you have multiple panels of slab, always do a set slab type automatically, because that is what will help you to pick the actual case of that particular slab. You can see now I have case 9. It's because I have done set slab type automatically, or better still, if I have checked it, if I have modeled that, okay, this is the case, all 4 edges are discontinuous, and I come into the software and I now pick the case I want it to be from here. So always make sure you do set slab type automatically. If you don't do that, you risk having coefficient that will be picked by the software, and those coefficient will not be what it should be, as you have not set the case for the slabs. Because by the time you click slab, it's showing me 1. So by the time I insert into multiple bays or panels, 1 is the case that is reading on it. So what it means is that by the time I do a slab strip in this direction and in this direction, the software will automatically pick the coefficient for case 1 for this case, and in that case you have a very lesser movement as opposed to the actual movement that you are supposed to have, because it will be picking the wrong coefficient for this case of this slab, which it will be different. So always do a set slab type automatically. Now, like I've said, I've modeled this, I'll do this. So let's now run the design. I have my slab strip in the long direction and in the short direction. Now if I do a slab analysis and design, let's say, okay, check design, do not modify. Of course I have set the load cases. So if I do a run design, now let's see. Now you can see now that the software in the long span, which is the X, in the long span we have coefficient 0 at the support, and we have coefficient 0.056 as the span, and this is the moment 10.4. Now let's check with what we have modeled here. Now this is the long span. Now we can see the coefficient in the long span from here, 0, 0 and 0.056. You can see what the software is also saying, 0, 0, 0 and 0, 0.56. You can see how similar it is, and you can check the movement as well. This is 10.4. So let's relate it in the long span. Let's relate it with what we have here in the long span. You can see we have 10.8, which is close. So at least you have a feel that, okay, you have done something right in this case. Now let's check the long span. You can see the coefficient 0, 0 and 0.076. Let's see what we have here. You see 0, 0, 0 and 0.0074. So you can see the closeness. And let's check the movement. The movement in the short span is 14.41. Let's check what's the movement here, 14.2. You can see how close these results are. So it gives you confidence that yes, something is going right as regard your design. By the time next time you take on an actual project, when you do this, you are sure that, okay, something is being done rightly. And you can see the equivalent UDL on the short span and equivalent UDL on the long span. So this is the result. You can see the reinforcement area 380, and for span here you have 309. Let's check our reinforcement area here for this 337 and 285. So at least you have a feel that, okay, yes, this is something going right. So like I said, my aim is to share what I've discovered in while you use the software. And I'm doing it because I know it's something that many people are using out there, and they might not be aware of all these small things that affect the output of your design. Like I said, always do a set slab type automatically, because that will be the slab type will determine the coefficient, moment coefficient, that the software will calculate and use to run your slab reinforcement design. So always do a set slab type automatically, so that you will have the actual case of the slab you are designing. Now let's move on. Now what I want to show you is that, let's assume that I have a wall load that will be on my beam. This, I want to show you that in the software, oh, excuse me, in the software, by the time I check the analysis design, I've run the analysis. Let's see the analytical model. Now this is the analytical model. Now let's look at the load that is transferred from the beam. Now let's pick the load case here. I'm picking the actual full load case that I'm picking. Now you can see that the software, after the load decomposition using yield line method, you can see the load distributed on the beams. Now let's close this quickly. We will still come back to it. Do I even need to close that? I think it can stay on the screen. So let me come here. Yeah, definitely. Okay, so now if you click on this beam on the short span and you say edit member load, it shows you the load that is being transferred from the slab to the beams. And you can see now this is the G 12.18 and this is the Q 3.15. Now if you sum this up, this will give you 15.3 something thereabout. And you can see that we have that load here. Now on the long span, this one is saying 18. On the long span, okay, no, I don't do that. Now on the long span, let's see what we have. I think it will be 41, same 12.3. Now this variation, I assume, is as a result of the yield line load decomposition method that is being used on this in the software. So you might not have something similar in this case when you calculate it manually. So but in this case, what the software is saying, that the load is distributed equally on evenly on these beams. So that's the what the software is saying. If you check here, edit member load, you can see it's saying the same thing here. I cancel, I did edit member load, you can see it's saying the same thing. So it's saying 15 point. Let's do a quick sum up of that. Edit member load and calculator. Now if you do 12.18 plus 3.15. That's about 15.33. So 15.33, I close this, I minimize this. Let's come here now. I have from the software, excuse me, from the let's have a, I don't want to clean all this in case, so that we'll make reference to them. Now this is from my manual, and let's say this is from the software. Software. So let's have something like that. Now let's take one of the beams. Let's take this beam in this case as an example. The beam is 4.2. Now the load, what I want to show you basically is that there's a slight difference in the load that is transferred to the beams, and the load on the beam is now factored. So in essence, this is a load that is already being factored, and from our manual analysis we are saying is the load transferred is what now? 15.4. So the load transfer from the one is 15.4. now note that this load is already factored. In this case, it's also factored in the software in this case. So we are having 15.33. Now let's now say from the software we have a wall load on this beam already. So let's use the exact wall load. This is the member load. I have assumed 3.0 height, and this is the wall unit width for my wall, 3.8. I modeled a 225 mm wall with plastering on both face. That's how this came about, and that's how this thickness came about. Like I said, I won't go details into modeling. I'm sure you find enough video on YouTube that will take you through that. So this is my wall load on that beam, 11.42 as a result of, so wall load, now let's put it 11.42 wall load, 11.42. now I have 11.42. now let's also add self weight of the beams. So self weight of the beam is I have a edit member load. You see the self weight here. You can see self weight of the beam is 2.43. I have a 225 by 450 beam. So this is the self weight, 2.43. So I go back, I put 2.43, 2.43. I also have 2.43. now let's do a quick sum. Now also have it in mind that this load that is transferred from the slab is already factored. So what we do in the manual case is that we'll factor this load, this wall load, by 1.4. So we want to factor it by 1.4. So now it's factored. We also factor the self weight by 1.4. Now if we factor this will now give us the load on this beam, 4.2 beam. Now let's look at the label of this beam here. I think beam 3. Okay, fine. Beam 3. Beam 3. So the load on this beam as a result of our manual design. So let's do a quick calculation of this. We have 11.42 0.42 times 1.4, that gives us 15.988. Now let's add it plus bracket 2.43 times 1.4, I close bracket, equals 19.39. Now I now had already factored slab load on the beam, plus 15.4 equals 34.79. So this is my load on this beam, 34.79. Now in my manual analysis, this is the load that is supposed to be transferred on this, from this slab to this beam, including the wall load, including the self weight. This is the sum of the load that I should have. But now if you check the software, you are now having, using this load case, you are now having 41. And the question you ask that, how come 41? You know, my manual is saying it should be 34.79, and the software is saying 41. Whoa, what is happening? That's the purpose I'm making this video, to make you see what goes on behind, in the background of the software. Now this is what the software is actually doing. The software will add this and add this and add this, and now factor it by 1.4. Now mind you, this load is already factored from the slab. You now have your wall load and your self weight. So what the software does is that it adds all this up and now factor it by 1.4. So let's add 15.33 plus 11.42 plus 2.43 equals 29 multiplied by 1.4. You see, we have 40.852. 40.852. So if you approximate, that's like 41 kilonewton per meter, as against 34 kilonewton per meter. Voila. Now this is what happens in the background of the software. Now in this case, now yes, you are actually safe, because you are actually having an higher load than what it is if you had done it manually. Because manually you would have assumed that, okay, this is factored already, so I will just factor this wall load, factor this, and what I have is this. But what the software does is that the same factored load from the slab, you will just add it with the wall load and add it with the self weight of the beam and factor it, which gives you 41. And that is what you are seeing here, 41, 41, 41, 41, that is transferred to the beam. I hope I'm making sense. Again, my aim is that so that you don't leave your design to the software. You need to actually probe the software and see that, okay, what the software is giving you is in relation to what you assumed. So these are some of the small things I've noticed, and it doesn't stop here. It goes from one element to another element to another element, which I hope I will have enough strength to make the videos and make it available for you. Like I've said, I tried and used this 15 days trial software, to make all these videos. So I'll be posting it uh, bit by bit, so that you can have a feel of what is actually happening in the background of the software, and your confidence level can increase while you are using this software, for those that have valid licenses and whatnot. So now again, let's check the bending moment. That is another thing that is also what checking. Now you can see the bending moment for the beams. Now it's saying 60. Yeah, it's saying 97 for the long span, and for the short span 60 bonding. Now let's see from here now. uh I hope I can clean this. Permit me, please, so that I'll have space to show you one more stuff before I end this session. Sorry for the dot. So I hope I'm showing you things that you can go back and try yourself and see. Oh, I don't want to have many dots, so that I can have enough space. Pardon me for the delay. So now, what I want to show you now, if I'm having a bending moment like this. Now the normal bending moment is W L square over 8. Now if I use this WL square over 8 for now, uh, have it in mind that what the load is saying is 41 from the software. So this is what we'll be working with, and not this for this case I want to show you. Now if you have this bending moment WL square over 8, if you actually calculate that, you have that's 41 times 4.2 times 4.2 equals divided by 8. So you have 90 for the short span. In this case, we have 90 kilonewton meter, that's moment. But now in the software is saying this is fixed, as the case is, from the connectivity of this slab to this column, the beam to this column, beam to this. So the software is saying it is fixed. Now in this case, now you cannot use this maximum moment, because you have some fixed end moment here and fixed end moment here. So in this case, let's say you use W S square over 12. Let's say 12. In this case, let's see what we will have. If you have 41 times 4.2 times 4.2 equals divided by 12, let's see, voila, you see we have 60.27 kilonewton meter. Now you can see that this is exactly what the software is having. Now in this case, you can see 60.62, which is close to what we have here, 60.27. So now when you look at the software is already telling you that there's actually a movement here and a movement here, as a result of the fixity of this beam to these columns and the beams. So let's say you now have so that means your movement sorry, your movement diagram is now like this, instead of this case, which would be like this, because you have more movement here. Now I don't know if we can apply this. Let's say we now have a 30% movement redistribution. That is the maximum allowed from the code. 30% movement redistribution. So I say 90 times 0.3 is equals to this, minus 90 is equals to 63. So when you do moment redistribution, so your span moment here will now be 63. Then redistributed moment will go to the top, which is 27 divided by 2. So you have 13.5 here, 13.5 here. So in this case, at least with this, what I have showed, you can see that there's actually a lot going behind in the background of the software, that if you don't probe the software to actually understand what the software is doing, you might be churning out designs that they will actually use for execution, and in your assumption, you might have thought that, okay, the software has done everything for you, take the result, go and execute. So I hope with this and the couple of videos I'll be posting, you'll be able to probe the software for some of the assumptions that you make while you are making your general arrangement, and you are putting it into the software to design for you. So please like and subscribe and share to as many people as possible, so that they will have a second thought, or a second approach, or a total revised approach of using this software for their design, because there's actually a lot that is going on in the background of the software that I will be sharing with you. So please like and subscribe. If you like this video, it will motivate me to post subsequent videos on other elements and the things that I noticed while using this particular software. So thank you for watching. Please like and subscribe, as I've said. And also, if you notice anything, you can actually send comment on it, or send me an email. I will be glad to discuss with you. Thank you for watching, and bye for now.